Hello, everyone. My name is Huanfa, and I'm going to give a brief introduction about our work on intelligent patrolling. So, as we all know, patrolling plays an important role in urban security, crime prevention, and response to calls for service. And as Tao has introduced, intelligent patrolling is important to make their work more effective. So, specifically, we have in order to understand how officers create guardianship and coverage, which is useful for strategic officers and strategic planning, we have developed an agent-based model of police tasking and movement. And in order to aid the route planning of police patrol, which is useful for frontline officers, we have also proposed a real-time cooperative patrol routing strategy. So first, my colleague Sarah will introduce her work on model of policing.
Thanks so much. Hello all. So I wanted to give some context for what an agent-based model actually is. An agent-based model is a system in which you understand the functioning of a higher level of a system by simulating the dynamics at a lower level. So if you wanted to understand traffic and where do you get traffic jams and this sort of thing, you understand that by simulating the individual cars speeding up, slowing down, getting off at different exits on the highway. So from these lower level behaviors, you get this higher level emergent phenomenon. So in the case of our work, what we're interested in is how are the individual police officers with their roles, with their assignments, with their various behaviors and the movements and the interactions they have with one another, how are those all coming together in order to, at a higher level, produce guardianship? How do we get from the individual officers to phenomenon like coverage? How do we understand visibility and presence based on the interactions of these individuals? So what we've done here is we've simulated the system. We're simulating officers in their vehicles moving around the environment and creating coverage and guardianship. Here in particular, based on our interviews and conversations with the officers, we have identified 3 different roles which generally can encompass a lot of things that officers are asked to do. So these are the response car, the report car, and the transport van. The response car is the one that is the response officers. So they're responding to urgent calls for service. So the nearest available vehicle will be called to attend to an urgent or IRS grade call for service. The report car is systematically going around dealing with less urgent calls for service, but can be pulled also to deal with more urgent calls for service if there's need. The transport van, on the other hand, is responsible for coordinating with officers who have apprehended a potential suspect. So there's the cooperation between the transport van and the officers who are responding to these calls for service. So these 3 different roles have some number of interactions, and I'm going to go into and give an example of exactly what that entails for one of these roles. But these are some of the behaviors that structure the way that officers move around the environment trying to carry out their assignments. Officers begin their shifts at a station, and they return to the station at the end of the shift. They may also return to the station at points within the course of the shift, which again I'll go into. And finally, at the point in the model that I'm showing you and in the video that you're going to see, the patrolling is very simplistically designed. We assume that the officers pick a random location and drive to it unless they're interrupted by a call for service. This is something which, again, Huanfa will give context for how that can be clarified and refined into something that's a little bit more meaningful, but it's a pretty good first step. So to give you a sense of when I say a response car role, what do I mean that this individual officer is doing? What I say is, you have a car. The car is patrolling, going around the environment, just sort of creating coverage in general. If it gets a call from the command and control center, it finds out that it's dispatched to an incident. It goes to the incident site. So this is blue lights and sirens. It's not it's not stopping for traffic lights, and it's moving along roads with the understanding that they can bypass certain amounts of traffic. They arrive at the site of the incident and they deal with it, based with a cost drawn from the actual incident. And if they need a transport vehicle because they've apprehended a suspect, they wait until the transport vehicle arrives. If they don't need a transport vehicle, but they do need to go back to the station to make a report, which is probabilistically determined, they'll do that and they'll return to the station. Otherwise, if they have needed a transport van, they obviously need to go back to the station to explain why they've apprehended this person. From that point, that they have either decided they don't need to make a report or they've returned to the station and made their report, they return back to the role of patrolling until they are once again dispatched to another incident. So it's a very simple set of behaviors, for example, in this case, of the response car role, but you end up getting some fairly interesting, yeah, this is being, let's see, there we go. We're going to show you a video that is an example of how they sort of end up moving around. So the road network is shown in black, and the police stations are also in black. The various different blues here are officers with different roles. And you see them moving around the environment creating guardianship. In particular, we're able to take away the road network and show how recently any officer has driven down a specific road. So you're able to visualize which roads have been covered in a fairly recent context, which roads haven't. It's possible to extract a lot of information from this depending on what you're really interested in. So are you interested in individual roads? Are you interested in regions? So there's a lot of context that you can get from this depending on what it is precisely that you're trying to measure to optimize for your specific borough. So it's quite flexible. At the end of it, you can get a sense of what roads do officers specifically utilize most, what do they drive on less, and then you can partition this by anything that you like. So you're able to fine-grain this a little and say whether officers are specifically driving down something in response to a call for service, or whether they're patrolling down the road with the understanding that the activity with which they're doing it influences the way that they're perceived and the way that they're able to create guardianship in the area. So at this point, Huanfa is going to talk a little bit more about the work he's done with the patrol routing strategy. So.
Okay, let's now move to the routing strategy. So, yep, hotspot patrolling has gained much attention as a means to deter crime. It mainly focuses on small areas with high crime rates. But to put hotspot patrolling into practice, we need a detailed routing strategy, especially when the hotspots are many and the patrol forces to use are limited. So the more specific question is, given the hotspot map from the predicted placing, how do officers move or travel among these hotspots to cover these hotspots regularly and fairly? So we have developed a Bayesian ant-based patrolling strategy to solve this problem. So the idea is from the ant behaviors. When ants are searching for food, they will lay pheromone on the routes to the food source. So the route with more pheromone levels will be more likely to lead to food source. Similarly, for patrolling, we can use the pheromone level to mark the visits to the crime hotspots. So when officers are deciding which hotspot to cover next, they can go to the hotspots with less pheromone because they're less visited. In this way, they can cover the hotspots regularly and fairly. And meanwhile, they'll consider other factors like the distance to the hotspots or the movements of his teammates. So how does this model work? In order to assess the performance, we conducted a case study in Camden Borough. We used the agent-based simulation technique, which is similar to Sarah's work. And the hotspot map used is the top 5% segments with the highest crime density. And we varied the total number of patrol units from 12 to 84 with 2 patrollers per unit. And we compare the strategy of BAPS we have developed and a benchmark strategy called CCPS, which is a cyclic strategy. Before we go into the results, I would like to introduce some important measures. So we use the idleness of hotspots to represent the time lag between 2 consecutive visits. For example, this is a map with 3 hotspots, and here are the visit times to each hotspot and the corresponding idleness. In this way, we can calculate the average idleness to each hotspot and the global average idleness to all of them. And to quantify the randomness of patrolling, we can calculate the standard deviation of idleness for each hotspot and the average standard deviation of idleness. So in order to measure the performance of the routing strategy, we have proposed a set of guidelines and measures. I will introduce 2 of them, the efficiency and the unpredictability. The efficiency is used to cover the hotspots fairly and regularly. and the measure is the global average idleness. Note that the low global average idleness value means high efficiency. For example, in this patrolling, the hotspots are covered regularly and fairly, which is good, so the GAI value will be low. On the contrary, when the hotspots are not covered regularly, like the hotspot C is covered very frequently in the beginning, but rarely in the later period, or hotspot C is never covered, then the global average idleness will be very high. So let's come back to the case study. We compare BAPS and CCPS using the global average idleness, and we can find out that using different team size, the BAPS has lower GAI value than CCPS. So we can say that BAPS has higher efficiency than CCPS. But a completely regular visit is not a good thing. So we use the unpredictability to prevent the offenders from being familiar with the patrol routes or the patrol visits. The measure is the average standard deviation of idleness. And note that the high average standard deviation of idleness value means higher predictability, which is good. For example, in this patrolling, the patrol visits are quite random, so the offenders will find it difficult to predict when the next patrol visit will come. However, if the patrol visits are very regular and easy to predict, the offenders will be happy because he can find the right time to rob or steal. So let's come back to the case study. We use it to measure BAPS and CCPS, and we find out that using different team size, the patrolling of BAPS has higher average standard deviation of idleness than CCPS. So we can say that BAPS has higher unpredictability than CCPS. So the BAPS patrol routing strategy covers different aspects of the patrol routine. A short conclusion about our work. So we have developed a model of policing, which is a bottom-up approach to understand how the guardianship is created. And it can be a useful tool for simulating the impact of changes of patrolling behaviors or the changes of the number or the locations of the police stations. Also, we developed a real-time patrol routing strategy to tell the officers how to cover these hotspots more effectively. It can be a tool to aid the route planning of patrol operations. To showcase the BAPS strategy, we developed a demo. This is the interface. So if you're interested, you can go to my demo session and we will show the demo for at least twice. Thank you for your attention.
Thank you. Are there any questions?
Hi, interesting talk. Just based on David Stringer's talk earlier, he was talking about that probably the biggest thing that's of the police officer's role is actually about creating confidence in society. So I wondered, how would you adapt what you're doing sort of from hotspot policing to, say, optimizing confidence in society? Is that possible, or is that...
I was particularly enjoying the dramatic roll of thunder during your question. So yeah, no, I think. Right. I mean, if you want to answer, that's more.
Thank you. This is a very good question. So yeah, sorry, we haven't considered increasing the public confidence in our work now, but that's definitely our future research direction because, as David has introduced, public confidence is very important, and it is key to the performance of the patrolling. So,
one thing I might add to that is actually that it's definitely possible that because we're able to know the activities of the officers as they're moving around, We know that certain activities are more associated with officer confidence. The different kinds of interactions have a very big influence on how people interact with their officers and how they view their officers. So by having a more fine-grained understanding of specifically how are people perceiving their officers, what level of visibility are they achieving, to whom and at what times and in what sense, you are actually able to get a much more detailed understanding of what's happening. So it would absolutely be possible to sort of say, well, if we tried this patrol strategy versus that patrol strategy, perhaps you would have marginally faster response times, but no one would ever see the police officer. So actually, if they take this slightly less efficient route, when they're sort of walking to their next patrol point, you actually have much higher visibility, and that increases confidence in some fashion. So based on the granularity of your understanding of what actually does functionally increase confidence, you are actually able to optimize and tailor the service that's provided to that, if that's something that is of interest to you. So that's well within the capability of the model as we've designed it.
Yeah.
So.
Any other questions?
Hi, the borough you used there was Camden, right?
Sorry,
Camden.
yeah, Camden?
Okay, where I live on my side is Islington, and on the opposite side is Camden. So you know the question I'm coming with. You can do the efficiency part for Camden, but how can you do the effectiveness part to show that when you do Camden and Islington together, you will be more cost effective? You will be more efficient.
So this is one of the really great things about agent-based modeling, is that we have, because what we've modeled it is on the level of the individual officers carrying out their responsibilities together, and in relation to the command and control center, you're able to scale up the area that you're modeling, and you're able to scale up the number of officers who have their unique sets of tasks and responsibilities. So it's very easy to incorporate that into the model, and indeed, it's really designed so that it can be scaled up for potentially the entire London area. Officers are fulfilling their responsibilities, which are locally specific, but as a result, you're able to simulate all of the different boroughs interacting or not interacting, as the case may be, and sharing information or not sharing information, as the case may be. So again, this methodology is very well suited to addressing those kinds of questions, and those boundary questions are some of the most frustrating, especially so the different boroughs collaborating, and especially also potential offenders moving between boroughs within the course of a shift, and the frustrations of following offenders between. So basically, if you have this kind of technology where you can understand everyone interacting and cooperating, you can actually get a much better sense of these separate boroughs and how their work translates together into guardianship. So yeah, that's a really important and good question, and we can do that. So.
Okay, thank you very much, Sarah. Thanks.